Can I meet with you at office hours at like two something today?
1:30 to 2.
Dr. Wan's class ends at 1:50. That's why I asked.
Oh, okay. I can extend them a little past 2.
All right, thank you.
Sure. Okay. So we're coming to chapter 4 now, which is all about vector spaces. It's a more theoretic part of the course than the first 3 chapters were. A lot of what's in the first 3 chapters is sort of computational. And while there is a computational aspect to chapter 4, I would say that there's um, probably a more theoretic bent. Now, very early in the course, I talked about, what's that? Very early in the course, I talked a little bit about the question about what a vector is. And we said really that the only good definition for a vector is that it is an element of a vector space. So let's review the definition of what a vector space is. So this is section 4.1. So vector spaces and subspaces. A vector space V is a non-empty, so there has to be at least one vector in it, collection or set of vectors. So we have a non-empty set of these objects called vectors, upon which we define 2 operations. Vector addition and scalar multiplication. So, you already have a good idea of what vector addition is all about when we're talking about vectors in Rn. And you already have a good idea of what scalar multiplication is all about when we're talking about vectors in Rn. So the scalars so in this course, the real numbers are what's known as the underlying field. So we can have vector spaces where the underlying field is the rational numbers. That's another perfectly nice field. Or the complex numbers. That's a perfectly nice field. You can't use something like the integers. That's not a field. if none of these words are, if field and the idea of what a field is not making sense to you right now, it's because it shouldn't, unless you've already taken Math 360 abstract algebra, which it's hard to believe that you'd want to take abstract algebra before you take linear algebra. Linear algebra is a much nicer way to dip your toes into the idea of algebra than just jumping into abstract algebra right away. But hopefully after linear algebra, you will have a good feeling about what an algebraic object is all about. And a vector space is an algebraic object. So let's go ahead and define what, the rules for the game of vector spaces.
Hey, Dr. O, can you repeat what's said on the board? It's kind of blurry.
Oh, sure. Which part?
All of it. All of it's blurry.
Just look at this. Yeah, why is that so blurry? Okay. Sorry. So vector spaces and subspaces. So a vector space V is a non-empty set of vectors upon which we define two operations: vector addition and scalar multiplication. So the scalars, and in this course, all the scalars will be real numbers, are what is known as the underlying field. So we're going to define the rules now for the game of vector spaces. So for all, let's see, how many do I need? C, D. So for all vectors U, V, and W in your vector space, in V, capital V, and for all scalars C and D in, let's see, in the real numbers for now, but in other courses you might have vector spaces over complex numbers or something else, but C and D are going to be our scalars. This is going to be the numbers. We have the following properties. If you take two vectors and you add them, you end up with another vector in your vector space. So if two vectors, U and V, are in your vector space and you add them, you end up with a vector in your vector space. U plus V is the same as V plus U. The order in which you add vectors doesn't matter. Now, you know this already from addition of vectors in Rn. It makes sense with the parallelogram law, and you know how to add vectors algebraically in Rn, and it makes sense with that too. U plus V plus W, where you add the U and the V first, is the same as U plus V plus W, where you add the V and the W first. So there exists a vector which we'll denote as 0 in our vector space, such that, so I'm going to abbreviate such that ST, 0 plus U equals U plus 0, which equals U, for all u in for all u in v. So there is a vector which we'll call the zero vector, such that when you add it to any other vector, it doesn't change anything. For all u in our vector space, there exists a vector which we'll call minus u, such that u plus minus u, which equals minus u plus u, equals the zero vector. So every vector has a negative.
Such that u plus what?
U plus negative u. Is that blurry?
Yeah, the whole screen is really blurry.
That's really weird. Hang on, let's see if I can fix this. Nope. Let's try to open this a little bit. Did that make any difference or not really?
No.
Huh. Okay, let me try something a little bit more drastic. Give me a sec. Is that better? Is that worse?
I think it might be better.
It looks like it's still slightly unfocused.
Hang on. So if I stand out of the picture, still unfocused. I'm using a completely different camera now. Huh. This must be very frustrating for you, and I apologize. Is that any better at all or not really? Let me try again. Hang on. So let's see. I'm getting more of the board now, so I can move this forwards. Is this getting any better or not really?
I think it's a little bit more readable than before.
Okay. I really don't know what's going on, unless it's just that the blackboard is getting so dusty. Well, okay. Let me know if something is not visible, and I'll do my best to make it as visible as I can. Okay. So basically 1 through 5 handle scalar, handle vector addition. 6 through 10 are more to do with scalar multiplication and the connection between scalar multiplication and vector addition. So C times U is an element of V. So if U is an element of V and you take a scalar multiple, that will be an element of V also. C
u plus v equals cu plus cv. In other words, scalar multiplication distributes over vector addition. And c plus d times u equals cu plus du. So scalar multiplication distributes over scalar addition. CD U, that's probably not very clear. C du written like that is going to be the same as CD times U. And lastly, 1 times U equals U. Those are the rules for the game of vectors, the axioms of vector spaces. And a lot of these have names. We call this closure of vector addition. And we call this commutivity of vector addition. Commutative property. This is associativity of vector addition. This one we would call the existence of a zero vector. This one we would call the existence of negatives. This again is closure. Closure this time of scalar multiplication. I'm not going to make you memorize these names. I am just trying to familiarize you with them because for those of you going on to take Math 360, you'll see a lot of this kind of thing. As you study the various algebraic structures there. So vector spaces are most people's first algebraic structure. And the nice thing about vector spaces is in a sense, they're very concrete because we have this lovely concrete idea of what a vector space is in Rn, even though those aren't all the vector spaces. And that's part of the point of this chapter. We're going to be able to do something a lot more general than that. But in Math 360, you'll study things called groups, which are very, very interesting objects. And you'll study things called rings, which are also interesting objects, and fields. The real numbers are a field. So are the complex numbers. So are the rational numbers. These are all fields, and there are plenty of others. So any set which has vector addition and scalar multiplication, which follows these properties, is a vector space. So examples of vector spaces. Examples of vector spaces. R for R2, R3, all these vector spaces we've been talking about so far. So R2 is, remember, it's just a set of all vectors x1, x2, such that x1, x2 are both real numbers. It's all the vectors which have just 2 entries in them. R3 would be all the vectors which have 3 entries in them, and so on. R4 would be all the vectors with 4 entries in them. R1 would be just the vectors with 1 entry in them, and so on. These are all the vector spaces we've talked about so far, but they're not the only ones. Let me give you another one. So let's let n be a whole number. Then P sub n is a set of all polynomials of degree at most n. So hopefully you have all these in your notes now, the fuzziness notwithstanding.
All polynomials.
All polynomials of degree at most n. It's that blurry. I don't know what's going on.
I mean, it might be your internet connection
Huh.
if it's not you, Kelly.
Yeah, because it looks, I mean, it looks a little blurry on my screen, but I can still read it. If it looks much blurrier on your screen, it's, yeah, it must be my internet connection, which is strange because the campus has pretty good internet generally. Well, at any point, if it's not clear, stop me and I will read it to you. So, for example, P2 are all polynomials of degree at most 2. So, you know, f of x equals x squared plus 3x plus 5 is in P2. Oops. And g of x equals, let's say, 4x minus 8 is also in P2. These are they're polynomials. There's things that you would study in a calculus or a pre-calculus course, but they are vectors in this space. I could take these 2 things and add them. You know how to add vectors. You just add component-wise. So x squared, there's no x squared term here, so we have x squared. 3x plus 4x is 7x. 5 minus 8 is minus 3. So f plus g is a vector in the space. So it's closed. If you take any 2 polynomials of degree at most 2 and you add them, you're going to end up with a polynomial of degree at most 2. It doesn't matter the order in which I add these vectors. So axiom 2 holds, and let's see, if I had a third one, it wouldn't matter how I group them. You can add them in any, you know, you can group any way you want when you add. So all these polynomials of degree at most 2 form a vector space. I could take a polynomial like f and multiply it by, you know, 4. 4 times f of x. You know how to take a polynomial and multiply it by 4. It's 4x squared plus 3 times 4 is 12x. 5 times 4 is 20. So all the axioms 1 through 10 hold for the set of all polynomials with degree at most 2. I can take polynomials and add them. I can do scalar multiplication. Scalar multiplication distributes over vector addition. So P2 is a perfectly nice set of, it's a perfectly nice vector space. Now you might be looking at your, thinking to yourself, wait a minute, well, P2 looks a lot like R3 because instead of writing x squared plus 3x plus 5, in other words, 1x squared plus 3x plus 5, that looks a lot like the vector 1, 3, 5. And the vector g of x equals 4x plus 8 has 0 x squareds and 4 x's and 8 ones. And so they add a lot, the vector space P2 acts a lot like the vector space R3. And if you think that, that's right. That's certainly true. They're very similar. They're both what are called three-dimensional vector spaces. Let me give you another one. So P2 is a perfectly nice vector space. Does everybody understand what, before I go on, does everybody understand what I'm saying here? That I can take two polynomials and add them, and I can take a polynomial and do scalar multiplication, and that addition and that scalar multiplication acts just like vector addition and scalar multiplication does for vectors in Rn? Is everybody okay with that? Can you give me a thumbs up or a thumbs down? Thumbs up, thumbs up. Okay, I will go on then.
What does it say in the on the right? Does it say 018 next to the 135? Yeah.
048.
048.
Yeah,
Okay.
because g of x is 0x squared plus 4x plus 8. So it just turning that into like a vector in R3. What I was saying is that these vectors in P2 act a lot like vectors in R3. They each have like 3 components, which is an observation you may have made for yourself. So how about we talk about, I'll just call this R infinity. Oops, I don't know where the 8 came from. R infinity. Actually, if you'll forgive me, I'm going to change the name. I'm going to call it R superscript n, just so it doesn't get ambiguous. And R superscript n will be just like R2 or R3 or R4, where each of those, like R2 has 2 components and R3 has 3 components and R4 has 4 components. This will have like infinitely many components. So this goes on forever. Has like an x1 component and an x2 component and a 3rd component and a 4th component and so on, but forever. And instead of writing it vertically, I can write it horizontally if I want. Usually when you write a vector horizontally, like if I want to write the vector x1, x2 horizontally, if this is like a physics class, I'll do it with parentheses, x1, x2. So usually that means that, just a way of putting it so it fits nicely on one line. So instead of writing it like this, I can write x1, x2, x3, x4, going on forever. And if I take 2 of these vectors and add them, they add pretty much the way you would want them to. So if I take the vector x1, x2, x3, and so on forever, and add it to the vector y1, y2, y3, going on forever, you just take the first components and add them, x1 plus y1. You take the second components and add them, x2 plus y2. You take the third components and add them, x3 plus y3, and so on forever. if I take a vector x1, x2, x3, and so on forever, and I multiply it by a number c. You know how to take a vector and multiply it by a number. You just multiply every component by the number. So this is just c times, oops, parentheses in the wrong space. C times x1, c times x2, c times x3, and so on forever. So we're getting a little ahead of ourselves, but this is what's known as an infinite dimensional vector space. We haven't even defined what dimension is yet. But if you accept that R2 is a two-dimensional vector space, anything with two components is a two-dimensional vector space, anything with three components is like a three-dimensional vector space, this has infinite many components. So I think it probably makes sense that this is an infinite dimensional vector space. So there are so many different vector spaces. We've barely scratched the surface when we've talked about R2, R3, and R4, and so on. Let's see. Let me talk about what a subspace is. Given a vector space V, a subspace H of V is a subset of V. So we're going to take some of the vectors in V that has three properties. The zero vector is in H. So one of the vectors you have to take is the zero vector. H must be closed under vector addition. In other words, if U and V are two of the vectors that you choose out of V to be in H, then U plus V must also be in H. And last, H must be closed under scalar multiplication. So in other words, if U is in H and C is a real number, then C times U is in H. So let's take a look at some subsets of vector spaces. So let's let V be the vector space R2. So all the vectors of the form x1, x2, such that x1 and x2 are real numbers. So a vector space we've been working with all semester. All those arrows in R2. Let's say H equals the 0 vector. So we were going to take some of these vectors now. The 0 vector. And also the vector 1, 0. So we're just going to take two vectors. Is H a subspace of R2? Remember, three things have to be true. Certainly the 0 vector's in there. We took the 0 vector. Is it closed under vector addition? If I pick two elements in R2 and add them, sorry, if I pick two elements in this set and add them, do I necessarily get an element in that set? So if I pick U to be one of these and V to be one of these, and it could be the same one, and I add them, is it necessarily one of these vectors? Right, it's not. It's definitely not. So the answer to this is no. H is not closed under vector addition. Give me an example of a vector I could choose here and another vector I could choose here, which could possibly be the same vector, such when you add them, I don't get one of the vectors in the set.
1, 0 plus 1, 0.
Yeah, 1, 0 plus 1, 0. So 1, 0 plus 1, 0 equals 2, 0. And these are both in H, but this is not. Let's try again. So this is definitely not, this is a subset of R2, but it's definitely not a subspace. So hopefully you have this copy down. And again, I am terribly sorry about the fact that it's so blurry. I don't know what to do. So how about this? Say H equals 0, 0, 1, 0, 2, 0, 3, 0, forever. So 4 zeros in there, 5, 0, 6, 0, 7, 0, and so on. Is H a subspace of our original vector space R2? So let's go through the three conditions. So certainly 0 is in there. And it does seem to be closed under vector addition, right? And you know, if I take so let's let A 0 and B 0 both be in H. So that tells me that A and B are both whole numbers. So A and B are both whole numbers. Let's n sub 0 or W is sometimes used for the whole numbers. 0, 1, 2, 3, and so on. And we know what happens if I add these two. A0 plus B0 equals A plus B, 0. And if A and B are both whole numbers, then their sum is a whole number. So it's certainly closed under vector addition. So axioms 1 and 2 hold. The 0 vector is in there, and it's closed under vector addition. Is it closed under scalar multiplication? If I take a vector that's in there and multiply it by a scalar, a real number, is that necessarily in there? If I take one of these vectors and multiply it by a real number, is what I get necessarily in that set? No, excellent, it's not. So, but H is not closed under scalar multiplication. It's not closed under scalar multiplication. For instance, 1/2, which is a perfectly nice real number, times 1, 0, and this is in H, equals 1/2 0, which is not in H. Oops, not in H. So we start off with something that is in H, you multiply it by a scalar, and you get something that's not in H. So it's not closed under scalar multiplication. So H is not a subspace of R2, which we call B. So far we haven't seen a subspace. Let's do another example. Say H, let's keep it small. So we'll include one vector. Is H a subspace of R2? Just the 0 vector. So certainly the 0 vector is in there. Is it closed under vector addition? If I take the 0 vector and add it to the 0 vector, what do I get?
0 vector.
The 0 vector.
Right, and if you scale and multiply, again, you end up with a 0 vector. So yeah, finally we've got one. So we have to check 3 things. So certainly the 0 vector is in H, because that's just 0, 0. And it's closed under scalar multiplication. So that's the first axiom. The second axiom, 0, 0 plus 0, 0 equals, so you carry the 7, 0, 0. So it's closed under vector addition. And c times the zero vector is just the zero vector. C times 0, C times 0. So it's closed under scalar multiplication. So the answer is a resounding yes. Finally, we got one. It's not a very big one. And this is how you show that a subset is a subspace. You check all three axioms. You make sure that the zero vector is in there, or you state that the zero vector is in there. You make sure it's closed under vector addition, and you make sure it's closed under scalar multiplication. How are we doing? Yeah. I don't think I'm going to get through another example in 4 minutes. So, again, very sorry about the blurriness issue. If it's my connection, then I'm not sure what I can do. I talk to IT, I guess. But hopefully, if that's what the problem is, then the recording, which is local, will be clear in case there are any board issues that are still causing problems. Is my face clear? So
Not
that's
really. Like
not
kind
re-
of, but
Kinda.
okay, because
Bit
to me
fuzzy.
my face looks perfectly clear. Okay, so it must be a connection issue. I'll email IT and see if they can give me a hand. All right, well, sorry about that. Hopefully whatever the issue is resolved for next time. I will see some of you in 13 minutes, and I will see others of you in more minutes. Bye, everyone.